All right, last section for you seniors. 2.5 measures of position. First, fractals. These are numbers that partition or divide an ordered set. It should be an ordered set, not and ordered set of data into equal parts. I think I fixed this in your notes, but not mine. An ordered set of data into equal parts. That's better. The median is a fractal because it divides the data into two separate parts. The three quartiles, Q1, Q2, and Q3, divide an ordered data set into four equal parts. So those work this way. About a fourth of the data fall on or below the first quartile. Then the second quartile, which is the median, about half of the data falls on or below the second one. Then 3/4 of the data will fall on or below the third quartile, and that's it. You have one quartile above that. So here we have an example. Number of nuclear power plants in the top 15 nuclear producing companies in the world are listed. Find the first, second, and third quartiles of the data set. What do you observe? So we have listed in order. Maybe. Hold on. All right, so list them out in order. You have 6, 7, 8, 9, 10. And 15, 16, 16, and 20, 20, 23, 33, 50, 58, and 104. Okay, so the easiest way to do this is to find the median first. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 numbers. So your median is going to be the 8th number. So that is Q2 right there. Then we should have 7 numbers above and 7 numbers below. So out of the 7 numbers below, the midway point of those is going to be your Q1. So that would be 9. Because you have 3 numbers below and 3 numbers above. Then your Q3 would be 33. Again, 3 numbers below Q3, 3 numbers above it. And that's all you have to do to find your quartiles. Let's do it in your calculator. Push stat, enter the data into L1, push stat again, then over to calc, push enter on OneVeristats, then scroll down, Q1 median and Q3 are all shown. So even easier way to do it. That way you don't have to organize your data at all. You just put it right in your list and it'll work out perfectly fine. Interquartile range, or IQR, is just a measure of variation that gives the range of the middle portion of the data. So the interquartile range is the difference between the third and first quartiles. So you find Q3, find Q1, then subtract them. That'll give you interquartile range. Interquartile range is important simply because you use it to find what an outlier actually is. So if you have a number that looks like it might be way higher than the rest of the data set, or you think it might be an outlier, you're going to want to use the interquartile range to figure out whether it's an outlier or not. So first you just find Q1 and Q3, then find interquartile range by doing Q3 minus Q1. You take that interquartile range and multiply it by 1.5. And whatever you get for that, you subtract from Q1, and any data entry that's lower than that is going to be an outlier. Then you add that interquartile range times 1.5 to Q3, and any data entry that's greater than that would be an outlier. Box and whisker plot. This is just a data analysis tool that highlights the important features of a data set. So you're going to have your minimum entry in there. That's your first point. Then your first quartile, Q1. Then the median, third quartile, Q3, and the maximum entry. Example 1. So the way I'm going to do this is I'm going to put all this into my calculator in L1 using the stat button. Alright, so let's enter this into our L1. Okay, then push stat again, calc, one var stats, and you just scroll down, and there you have your numbers. So your minimum is 24, Q1 is 28, the median is 35, Q3 is 41, and your max is 60. Now you got to draw a box and whisker plot. Now whenever you draw these, you have to do a number line underneath it in order for it to make any sense. And I'm not going to be real picky about your number lines, but you should at least start below the minimum. I'm going to call it 20, then 30, 40, 50, 60, and then I'll go up to 70 either. So my minimum is 24. So it's like right there. Then Q1 is 28. Call that there. Median is 35. It's like right there. Q3 is 41. And your max is 60. Okay, now that I have my little markers here, I can draw my lines, make it a little more official.
What did you say?
So I draw these lines. To finish my box and whisker plot out. And that's it. So that's how your box and whisker plot should look. This is a pretty easy section in general. All right, let's go backwards from what we just did. Use your box and whisker plot to give the 5-number summary for the data. So we have a men, and that's going to be at -35. We have a Q1, that's at -10. We have a median, that's at 15. You have Q3, that's at 30. And your max is at 40. Dang, none of you guys even told me bless you. So that's it. Percentiles and other fractals. You have quartiles, that divides the data set into 4 equal parts. Deciles, which divides it into 10 equal parts. And percentiles, which divides it into 100 equal parts. Really, all you have to think of the base words. Quartiles, a quarter is 1/4. Deciles, decade. Percentiles, century, 100 years. So, percentiles can be used to measure unusually high or low values. Children's growth measurements are often measured in percentiles. Lots of your state testing is measured in percentiles. SAT scores are measured in percentiles. Measurements in the 95th percentile and above are unusually high, while those in the 5th percentile are unusually low. All right, example 5, interpreting percentiles. The ogive at the right represents the cumulative frequency distribution for SAT scores of college-bound students in a recent year. So these are the class of 2010 SAT mathematics scores. Find and interpret the percentile rank of a student who scored 450. So basically you just go over to 450, to be like right here, and the percentile rank of that person would probably be about the 25th percentile or the 30th percentile. All right. What about the person who scored a 750 on the math portion of the test? That would be scoring here. And you can see how close they are to the to 100% as far as the cumulative relative frequency. So that's going to be up real high. And so they're going to be looking at like the 98th percentile. Then if Jan scored at the 44th percentile, what would her score be? If you look at this, that's going to come in like right here. So her score would be about a 500. To find the percentile that corresponds to a specific data entry, X, use the formula percentile of X equals the number of data entries less than X divided by the total number of data entries times 100. So you find the number of data entries that are less than X, then you divide by the total number of data entries. Next up is the standard score. Now the standard score, or the Z-score, any of you who take college statistics will see so much about the Z-score. Z-score represents the number of standard deviations that a value x lies from the mean. So to find the Z-score for a value, use the formula Z equals value minus mean divided by the standard deviation. So that's just x minus mu over sigma. It's important to realize that Z-scores can either be positive, negative, or zero, because it might be one standard deviation below, or two standard deviations below, or two standard deviations above. So it could be any number really, positive, negative, or zero. All right, let's find a Z-score here. The mean speed of vehicles along a stretch of highway is 56 miles per hour. That is your mu. Standard deviation is 4 miles per hour. That's your sigma. You measure the speeds of 3 cars traveling along this stretch of highway as 62, 47, and 56. Find the Z-score that corresponds to the speed. Okay, so the first Z-score would be Z equals 62 minus 56 over 4. 62 minus 56 is 6 over 4, so that would be 1.5. Your second one would be 47. So it would be Z equals 47 minus 56 over 4. Now 47 minus 56 is going to give you a negative 9 over 4. So that'll give you negative 2.25. Your last Z-score would be 56 minus 56 over 4. That's 0 divided by 4, which is just 0. Important part that I skipped is assuming the distribution of the speeds is approximately bell-shaped. That's when you really use your Z-scores, is when it's a bell-shaped curve. But anyhow, this tells you that 62 is 1.5 standard deviations above the mean. And so remember that 95% of our data falls within 2 standard deviations of the mean, right? So this person falls within our normal range of the mean. This person who's driving 47 is 2.25 standard deviations below the mean, which means that they're going to be falling in the bottom 2.5%. And then this person is driving exactly what our mean is, so there's 0 standard deviations in the mean. They are right in the middle of that bell curve. All right. So you might ask why it's important to figure out what a Z-score is. And a good example of this is whenever you're figuring out 2 sets of data, comparing them to each other. So if we just compare men's heights in the sigma, or the standard deviation, the mean for guys' heights is 69.9 inches, and the standard deviation is 3 inches, right? Women's heights is 64.3, and the standard deviation is 2.6 inches. And so if we were looking at a 6-foot-tall man and a 6-foot-tall woman, in order to compare how much taller they are than the normal person, we would have to compare them based on the averages. And so the average height for a man is 69.9 and a woman is 64.3. There's a significant difference there. But if we want to actually figure out how much different they are, then we need to use our z-scores. So 6 foot tall man, 6 foot tall is 72 inches. All right, and so if we're looking at the z-score for a 6 foot tall man, that would be 72 minus 69.9 divided by 3. And so we do exactly that, 72 minus 69.9. We divide that by 3. You're going to find that the guy who's 6 foot tall is 0.7 standard deviations above the mean. So he's not even 1 full standard deviation above the mean. Then the woman who's 6 foot tall, still 72 inches tall. The height of a 6 foot tall person doesn't change. Still 72 inches. Then you subtract the mean, 64.3, and divide by the standard deviation. (72) minus 64.3 . And you get 2.96. So she is almost 3 standard deviations above the norm. So if you look at the bell chart or your bell-shaped curve, oh, that was beautiful. Your mean is this number here in the middle, right? And then you have 1 standard deviation outside, above and below. Then 2 standard deviations would be out here. And so if we're looking at this data, this person at 0.7, this guy, is right here, right? So he falls within 1 standard deviation of the mean. So he falls within the normal 68% of guys. Okay? Then remember our next standard deviation out, which is 2 standard deviation, that contains 95% of people. So if you're more than 2 standard deviations out, you're already in the bottom, or so it's 5% left, right? So this down here, from here down would be 2.5%, and from here up would be 2.5%, right? This person is 2.96 standard deviations out, so this woman is like right out here, which puts her in the top 2% of women in the country. And so when we compare a 6 foot tall woman compared to a 6 foot tall guy, the guy falls right within the first standard deviation of the first 68% of people. So he's right in the middle. Whereas a woman who's 6 foot tall is way out on the end. She's far above the norm for women. Okay, I'm going to give you what exercises to do for your homework, and then you're going to have a chapter test next week. You are allowed to use your notes on the chapter test. Make sure you do use them. Okay, here's your homework for this. 1, 3, 7 through 10, 11, 14, 16, 18, 22, 25, 31 through 35, 40, 42 through 44, and 50. It's a pretty short assignment, really. when you look at how hard the questions are. It's going to be a lot of just typing stuff into your calculator, really. So do this assignment. Chapter test will be next week. Make sure you use your notes on it. I'll have to check and see how many of you are juniors. I think there's only one or two. So your class might be over. That's sad. But that's about it. Email me with any questions. And then I will obviously post a video of me going over this homework assignment too. All right, guys.